Chapter 2, problem number 16. An automobile starts from rest and accelerates to a final velocity in 2 stages along a straight road. Each stage occupies the same amount of time. Same time. Now, the car's acceleration in stage 1 is 3 meters per second squared. And we're told that the velocity at the end of stage 2 is 2.5 times greater than it is at the end of stage 1. Okay, so we have VF1, VF2 is equal to twice VF1. 2.5 times, excuse me. And the car starts from rest. So VO1 is 0. And we're asked to find the acceleration in stage 2. So, wrote down the given information, wrote down the unknown, drew a diagram. Now we're going to write our guide to thinking to get started. So we're looking for A2. So we could find A2 using the definition of acceleration. There we go. The final velocity, stage 2, minus the final velocity, stage 1, divided by the time. Now we know the final velocity in stage 2 is equal to 2.5 times the final velocity in stage 1. So now we have an equation with 1, 2, 3 unknowns. So we definitely need at least another equation. So I'm going to write an equation for the acceleration in stage 1. So A1, which we know, is equal to VF1, which we don't know, minus VO1, which is 0, divided by time. So here we have one equation, 3 unknowns. Here we have one equation, 3 unknowns. So let's see what we can do. Look at the problem, see if I'm missing anything. Okay, I'm going to solve this equation for VF1. So it will be in terms of A2, which we don't know, and time. And then if I substitute that into here, I'm hoping that I get time on both sides of this equation in the numerator, and it can cancel out. And I won't have VF1 anymore because I will have substituted in what this equation becomes when it's solve for VF1. And I see we know acceleration in stage 1. So I think that's going to work. So here we go. I guess I'll do that over here. So I'm going to first solve this for VF1. There we go. And now I'm going to substitute this into this expression. Okay, so let's see. I'm going to call this equation 2. No, let's call this equation 1. Doesn't matter in this equation 2. Okay, I just want to show this here so it's easy for the person reviewing this problem to know what I did next if they don't have me talking them through the problem. So what I'm going to do is I'm going to say substitute 1 into 2. Okay, so that's what that means. Take 1, put it into 2. So here we go. Acceleration 1 is equal to And yes, delta t appears on both sides. Actually, delta t is in the numerator on this side and the denominator, so that gets kicked out of town. So we have that a1. Actually, we're going to solve for a2. Right, that's the unknown. Is equal to a1 multiplied by 2.5 minus 1. So let's plug and chug. So a1 is 3 meters per second squared. 2.5 minus 1. So we're taking 3 times 1.5. And I get 4.5 meters per second squared. For Chapter 2, problem number 16, I'm now going to sketch the motion graphs. So here's the position versus time, velocity versus time, and acceleration versus time graphs. The time intervals are equal, so I'm going to say from here to here is delta t, and that's for the first part of the story, and then from here to here is another delta t. Now, the car accelerates from rest, so I'm going to draw a parabolic curve that starts out flat and has an ever-increasing slope. And then during the second time interval, it is another parabolic curve, but increases at a greater rate. The slope increases at a greater rate than the first one. So maybe something like that. Okay, so from here to here, we have greater acceleration than from here to here. So on the velocity time graph, that means during the first time interval, we need to show a straight line with a lower slope, a lesser slope, than during the second time interval. Okay, so it should be a straight line. Okay, let me use a ruler here. Here we have another straight line, but it's steeper. There we go. So this represents the increase in velocity during the second segment, and this represents the increase in velocity during the first segment. Then down here, we have an acceleration, a constant acceleration, so I draw a straight line horizontal during the first segment, and then during the second segment, we have a greater acceleration. Okay, so these are what we call sketches, motion graph sketches. You notice that I did not scale exactly. It was just very conceptual, we'll say. Okay, so it just gives you a feel for the motion. Okay, this is steeper than this. This is higher than this. This is a steeper parabolic curve than that. Now, what I did to draw these is I remembered that the slope of a position time graph gives you the velocity. So since we have a steadily increasing slope in this segment and in this segment, I wanted to show a constantly or steadily increasing velocity. So that's why these are straight lines. The slope of a velocity versus time graph gives us the acceleration. So here we have a constant slope. So I show a straight line parallel to the t-axis, right? Constant acceleration. Here we have a constant slope, but it's steeper than this one. So I show a straight line parallel to the t-axis, but higher up. Now, recall that the area under an acceleration versus time graph gives us the change in velocity. So if I found the area of this region here, let's call it A1, that should be equal to the change in velocity from here to here. So let's say this is VF1, and this is our VO1. So that should be equal to VF1 minus VO1. Likewise here. It would be the change in velocity from here to here. So this would be VF2 there. So this area, A2, would be equal to VF2 minus VF1. The area under a velocity versus time graph is equal to the displacement. So here we have a triangle. So I found the area of that triangle. Well, that would be 1/2 the base, which is delta t, multiplied by the height, which is VF1 minus VO1. And that should be equal to the displacement during the first segment of the car accelerating. And then that would also be true of this area here. So we have a triangle on top of a rectangle. So if you found that area by taking delta t multiplied by the height of the rectangle, VF1, plus the area of the right triangle, 1/2 the base, times the height, which would be VF2 minus VF1. That would be equal to the displacement of the car during segment 2. By the way, down here you might be wondering, well, why is the area equal to the change in velocity? Well, if you look here, the area of this rectangle, let me just do it here, would be the base, which is delta t, times the height, which is equal to A1. But isn't A1 times delta t, that is the acceleration during segment 1, don't confuse it with this A, capital A for area, multiplied by the time, well that's equal to delta V, the change in velocity.